Hare Krishna to everyone. So we'll start our ARM Cortex MX processor memory map. So this is our MCU, and this MCU is it is a 32 bit. 32 bit means we can access up to 2 to the power 32, means 4 GB of memory addresses. So that address is its starting address is from 0 cross 8 zeros to 0 cross 8F. Okay, and that addresses, it is here in this PPT. You can see that addresses, it is divided into different section. First is code section, second is SRAM section, third is peripheral section, fourth is external RAM, fifth is external device, sixth is private peripheral bus, and seventh is vendor specific memory. So it is divided into different section. First we'll explore the code section. The code section, it's having 0.5 GB, means 512 MB. That code section is connected to our embedded flash or OTP. Okay, so in that section you can store the vector table. So we'll explore that vector table while writing our startup code, how we can write our vector table. So, and the second is SRAM section. SRAM section is also having 512 MB, 0.5 GB, means and that 1 MB it is dedicated to your bit band region. Bit band region will explore while writing our firmware, while writing our code. We'll explore what is bit banding, and in the SRAM section you can execute the program. And third section is peripheral section. Peripheral section also 512 MB, means 0.5 GB, and also 1 MB is dedicated to bit band section. So that peripheral region, like in peripheral region you can access the registers of UART or GPIOs, or you can access the registers of I2C SPI, that peripherals. So that addresses you can access by bit banding. Okay, so and in the peripheral section you can't execute the code. If you are try to execute code, it will go into fault, so your code will stuck inside the while loop. So you can't if anyone try to execute code in the peripheral section, it will give you a fault. And our fourth section is external RAM. So that is size of 1 GB. So that much size it is given. Like if you are executing the application of if your interfaces the video or audio module, that time you can use that external RAM. You can, that much size is needed for recording your audio or recording your video. You can execute that program into the external RAM. And our fifth section is external device section. That is also having 1 GB of spaces. And our sixth one is private peripheral bus. It is also having a 0.5 GB. Okay, so that private peripheral, it is dedicated to your NVIC registers, NVIC and SysTick timer. And the last section is your vendor specific memory, that is also having a 512 MB, means 0.5 GB. So like that, our ARM Cortex MX processor is divided into the sections. So we'll explore the just open STM32F446X datasheet. In that datasheet, just search memory map. So this is our microcontroller memory map. This is the peripheral connected the buses. So first is APB1, APB2, HP1, and HP2 bus and HP3, and this is our internal peripheral. So you can see our peripheral starting address is 0 cross 400 0 to 0000. So, and that APB1 bus ending address is 0 cross 4007FFFF. Like that, different starting and ending addresses are there. So this is our peripheral map. In down section you can see they have mentioned the buses, and that buses, first one is APB1 bus, and our starting address of our peripheral, it is dedicated to a timer 2. Okay, so first loading address is 0 cross 40000000. It is dedicated to timer. Second section, it is dedicated to timer 3. Like that, likewise our APB bus dedicated to different peripherals. Like that, our APB2 also dedicated to different peripherals. So we need these addresses for while writing our code. So first we'll start with our GPIOs. So you can see our GPIO is connected to, it is hanging to our HP1 buses. So, and the starting address is 0 cross 4002. Okay, that it is hanging a GPIO, and likewise different addresses are there up to GPIOH we have. This is our STM32 F446 RE memory map.